Good day. Today we're going to continue to discuss the ratio of continuous random variables. So we have here, let x and y be continuous random variables. Let's find the CTF of the z equals y over x. We have, so in this case, we have to take note that you have the z should be uh, less than or equal to small letter z if and only if you have x, y is in the region of you have y over x, which is less than or equal to z. So in this case, if x, okay, so if the x is greater than 0, this is the set y, which is less than xz. Okay, then if uh, x is less than 0, then we could have that the y is greater than xz, meaning we could have that the f, okay, the function, okay, that's capital letter Z of small letter z would be, you have the p of z, which is less than or equal to z, which is also can be written as the integral of, you have the f of xy dx dy, where your xy would be uh, y over x, which is less than or equal to z. Okay, which implies that you have the integral of dx from negative infinity to 0 times the integral of the function xy dy. But in this case, that is from zx to positive infinity, plus you have the integral of dx from 0 to zx. Wrong. That should be that would be infinity. So infinity, and then multiplied by the integral of, you have the function of xy dy from negative infinity to zx to complete the cycle. Okay. So in other words, the density, okay, so density of z would be, you have the density of z would be equal to, you have the dfz over dz, okay, times z, which is equal to, you have d over dz, the integral of, you have dx from negative infinity to 0 times the integral of the f of xy dy from zx, that zx, to positive infinity, plus you have d over dz, integral of integral of dx, you have dx from 0 to infinity times the integral of f of xy dy from negative infinity to zx. In this case, we can calculate it using the differentiation under the integral sign rule, which can be expressed as, you have the f of z, which is equal to the integral of dx from negative infinity to 0. This is dx d over dz times times the integral of, you have the f of xy dy from zx to positive infinity, plus the integral of dx d over dz from 0 to infinity times the integral of f of xy dy from negative infinity to cx. So in this case, by the fundamental theorem of calculus and by chain rule of differentiation, we could have, um, in this case, we could have the d over dz um, times the integral of the function xy dy from zx to positive infinity is equal to the negative xf of the x zx. And in another, since we have two cases, then you have the d over dz times the integral of the function xy times xy dy from negative infinity to zx is equal to x of f of xf of x zx. Therefore, we could have that the function, this is capital letter Z, small letter z, is equal to the negative integral of xf of x zy dx from negative infinity to 0 plus uh, the integral of xf x zx dx from 0 to infinity. In this case, we have that the negative x is equal to the absolute value of x for x less than 0, and the absolute value of x is equal to x for x greater than 0. Therefore, we could have the function is equal to the integral of dx, absolute value of x, f of x zx dx from negative infinity to infinity. And if x and y, in this case, if x and y are independent, we could have the um, cumulative density function of z would be the integral of absolute value of x, okay, times the function of x, the cumulative function of x times the cumulative function of y in terms of z x dx from negative infinity to positive infinity. Okay, so let's have the transformation of the joint density. So let x and y have the joint density xy, g of the r squared maps to r, and g sub 2 of r squared maps to r be two functions. Assume that u is equal to g sub 1 xy and v is equal to g sub 2 xy are two new random variables. So we have here the definition. Consider the matrix A. So you have ACD, ACBD, which are elements of the real numbers by 2 by 2. And the determinant of A is the determinant is equal to AD minus BC. So you have here, let the Jacobian UV is equal to the determinant of, you have that partial differentiation, okay, of h sub 1 over h sub 1, and then the other one you have over the partial differentiation of u. Then you have the partial differentiation of h sub 1 times the partial differentiation of v. And then you have the partial differentiation of h sub 2 over the partial differentiation of u. And then you have the partial differentiation of 2 over the partial differentiation of v. So this function is called the Jacobian of the vector function h. Okay, so h sub 1, h sub 2. It is calculated as the determinant of the matrix. Therefore, the Jacobian vector, okay, you have now the um, determinant. So we assume that the derivatives here exist and that the Jacobian vector matrix is not equal to 0 for all x and y. Okay, so let's have an example. Assume that x and y are independent and distributed uniformly in 0, 1. Let u is equal to x and v is equal to x plus y. Okay, so the joint density for u and v would be, okay, so in this case, to answer this one, we have to find the joint density for u and v, so we can use the transformation method. First, we need to find the inverse transformations, which will allow us to express x and y in terms of u and v. Since in this case, we could have um, u is equal to x. So the inverse transformation is simply x is equal to u. To find the inverse transformation of v, we solve for we solve for y in terms of x and v. So take note that v is equal to x plus y. Therefore, we could say that y is equal to v minus x. Now, we can substitute our inverse transformation into the joint density for x and y, which is just the product of their marginal densities, since they are independent and uniformly distributed. So in this case, we could have the f of xy would be equal to the f of x times f of y, which is in this case is equal to 1 times 1, which is equal to 1. We can substitute u for x and v minus x for y and use the Jacobian determinant to find the joint density for the u and v. Now, in this case, you have the um, f of u and v, which is equal to the function of xy. You have the absolute value of the Jacobian, where in this case, the Jacobian, the absolute value of the Jacobian is equal to, you have the determinant of, you have the matrix. So you have the partial differentiation of x over the partial differentiation of u. Then you have the partial differentiation of x over the partial differentiation of v. And then you have the partial differentiation of y over the partial differentiation of u, and then the partial differentiation of y over the partial differentiation of v. Okay, so in this case, we could have, since you have okay, so in this case, it's clearly that determinant, we can now have this one as the partial differentiation of this is 1, the partial differentiation of this one is 0, and then this is -1, and this is 1. Okay, which is, if we are going to get the determinant of this one is equal to um 1. Okay, therefore, if going back here, we could have that the function uh, uv, which is equal to the function of xy times the Jacobian, is equal to, this is from here, this is 1, and this one is also 1. In other words, which is equal to 1. Therefore, we could have the joint density, therefore, the, okay, the joint density for u and v is simply, you have the function of uv, which is equal to 1. For in this case, u should be greater than or equal to 0, but less than or equal to 1. And since you have x plus y, you could have the v should be should be greater than or equal to 0, but less than or equal to 2. So that's how we are going to solve for transformation of joint density. Thank you very much.